Welcome to the deep dive. And today, wow, we have a big one. We're going to try and tackle the mathematical language of crystal symmetry,
We are. We're talking about group theory.
which I think for a lot of people sounds incredibly abstract, almost unapproachable.
It does, but our mission today is to, turn this really dense chapter into something you can actually follow step by step. We want to show how these mathematical rules are, well, they're the blueprints for how crystals are built.
Right, because this isn't just math for math's sake. It directly predicts a material's properties, doesn't it?
It's the ultimate shortcut. Is it piezoelectric? Does it rotate light? The answer is all there, right in its symmetry group. We're going to connect that abstract geometry to real, tangible physics.
I think to get us in the right mindset, there's this quote from the mathematician Neumann that just captures it perfectly.
Oh, I love this quote.
Group theory is a branch of mathematics in which one does something to something and then compares the results with the result of doing the same thing to something else, or something else to the same thing.
I mean, it's so elegant. And for us in crystallography, the something we're doing is a symmetry operation, a rotation, a reflection.
And the something we're doing it to is the crystal structure itself.
Exactly. And we compare, does the crystal look exactly the same after we do it? Is it indistinguishable? If the answer is yes, then that operation, that doing something, is an element of the crystal symmetry group.
Okay, let's unpack that. Let's start with the absolute foundation. What does it even take for a collection of these operations to be called a group?
Right. What are the non-negotiable rules?
Let's get into it.
To make this real, let's ground it in an actual crystal. Quartz is the perfect example.
Why quartz?
Because all its symmetry elements, its axes of rotation, its mirror planes, they all intersect at a single unmoving point. And that is the very definition of a point group.
And the specific quartz structure we're looking at in the notation is called group 32, or D3 for molecular physicists.
Right. And this group is made up of exactly 6 symmetry operations. These 6 operations are the elements that form the group. We can just label them O0 through O5.
Okay, so what's the first one? O0.
O0 is always the identity operator. We call it E. It's the operation of doing nothing.
Doing nothing is an operation.
It has to be. It's the baseline, the starting point. It ensures the group is never empty.
Okay, so that's one. What about the others?
Well, for quartz, the main feature is a 3-fold rotation axis, right down the middle, the z-axis. So rotating by 120 degrees, or 2 pi over 3, that's our operator O1.
And if you do it again?
You get a 240-degree rotation, that's O2.
That makes sense. So we have do nothing, rotate 120, and rotate 240. What are the last three?
The last 3, O3, O4, and O5, are all 180-degree rotations, like flip around 3 different 2-fold axes.
And crucially, those 3 axes are perpendicular to that main z-axis, aren't they?
They have to be. And what's really fascinating, and this comes from Euler's theorem, is that you only need to define that z-axis in one of those perpendicular 2-fold axes. The other 2 are, they're automatically generated. The symmetry of the system demands their existence.
So there's our set of 6 elements. Now, You mentioned an operation on the group itself.
Yes, group multiplication, which sounds complicated, but it just means doing one operation after another, sequentially.
So if we write, say, OJ-OI.
That means you apply operator OI first, and then you follow it with operator OJ. The order matters.
Okay, let's try it. What if we do O1, or 120-degree rotation, and then we do O1 again?
Well, you've rotated 120 degrees, then another 120. That's a 240-degree rotation in total, which is just O2. So O1 times O1 equals O2.
Simple enough. And what if we do O1, the 120-degree turn, followed by O2, the 240-degree turn?
You get a full 360-degree rotation. You're right back where you started.
Which is the identity, O0.
Exactly. O1 times O2 equals E. And that right there, that shows you the concept of the inverse. O1 undoes O2 and O2 undoes O1. They're inverses of each other.
And what about those 180-degree flips, O3, 4, and 5?
They're all their own inverses. If you flip something 180 degrees and then you flip it 180 degrees again, you're back to the identity. They're self-inverse.
Okay, so we've seen it in action. Now let's get formal. This is where it gets really interesting for me, because these abstract rules you're about to describe, they physically constrain how matter can organize itself.
These are the 4 axioms. They are absolutely non-negotiable. Number 1 is closure.
Closure.
It means that if you take any 2 elements from your set, any 2 of our 6 quartz operations, and you multiply them, the result must also be an element that's already in the set.
You can't accidentally create a new 7th operation.
Never. The system has to be self-contained. You can't combine two valid symmetries and somehow break the overall symmetry of the crystal. That would be physically unstable.
That makes a lot of sense. A closed system.
Okay.
Okay, what's axiom 2?
Associativity. This one is a bit more about the math behind it. It just means when you're combining three or more operations, it doesn't matter how you group them.
So doing A then B, and then applying C to that result is the same as doing B then C, and applying A to that result.
Precisely. The final orientation of the crystal is identical. It ensures the math is consistent no matter how complex the sequence of operations gets.
Okay. And the third rule?
The existence of a unit element, which we've already met, it's E, our identity operator O0. There has to be a do-nothing operation in the set. It's the fundamental reference point.
And the last one?
The inverse element. For every single operation in the set, there must be another operation in that same set that undoes it.
A way to get back to the start.
Every turn must have a corresponding counter turn. It guarantees reversibility for the entire system.
Now, you mentioned that order matters. That brings up this idea of commutativity.
Right. If the order doesn't matter, if OI times OJ is always the same as OJ times OI, then we call that group an abelian group. It's commutative.
But for crystals, that's not always the case, is it?
Very often it's not. Our quartz example, group 32, is non-abelian. If you rotate 120 degrees around the vertical z-axis and then flip 180 degrees around a horizontal x-axis,
You end up in a different spot than if you did the flip first and then the rotation.
a completely different final position. And that non-mutativity is, it's a direct consequence of working with rotations in three-dimensional space. The geometry itself demands it.
So once we've confirmed a set follows these 4 rules, we can start to describe it. What's the first most basic property of a group?
Its size. We call it the order of a group, and we use the letter n. It's just the total number of distinct elements.
So for our quartz group, the order is 6.
N equals 6. And all the crystallographic point groups are finite groups, meaning they have a specific countable number of elements. That number n tells you how many different ways you can orient the crystal so that it looks identical.
Okay, that's order. Now, what about this idea that 2 different groups can have the same underlying structure?
That's isomorphism. It's a really powerful concept.
So what does it mean for 2 groups to be isomorphic?
It means there's a perfect one-to-one correspondence between their elements that preserves the entire structure. If you write out their multiplication tables, they will look identical.
Even if the elements themselves are totally different things, like one group is rotations of a crystal and the other is, I don't know, a set of matrices.
Exactly. If they're isomorphic, the abstract rules they follow are the same. This is why group theory is so universal. It's not about the physical thing. It's about the rules of the relationships between the elements.
And is homomorphism related to that?
It is, but it's less strict. It's more of a one-way street. If group S is homomorphic to group N, it means you can map elements from S onto N, and the structure is preserved, but it's not necessarily a one-to-one mapping.
So multiple things in the first group could map to the same single thing in the second group.
Right. Think of it like compressing information. You're simplifying the structure while still keeping the fundamental mathematical relationships intact.
Okay. And what about the simplest kinds of groups? The cyclic groups.
Cyclic groups, or CN, are the most basic. They're generated entirely by taking powers of a single element. We can call it O.
So for a group of order 3, for instance.
The elements would just be O to the power of 0, which is the identity, then O1 and O2. That single element generates the entire group. A pure threefold rotation axis is a perfect example of a cyclic group of order 3.
Which brings us to a more general idea, group generators.
Yes. This is absolutely key for doing this stuff on a computer. The generators are the absolute minimum number of elements you need to build the entire group.
A kind of recipe.
Exactly. You don't need to list all 48 operations for the most complex cubic group. You just need to define, say, 2 or 3 generator matrices and the rules for multiplying them, and the computer can construct the entire group from that minimal set. It's the ultimate mathematical shortcut.
And within these larger groups, we can often find smaller, complete groups hiding inside. Subgroups.
A subgroup is just a subset of elements from a larger group that, if you test it, satisfies all 4 group axioms on its own.
And if it's not just the do-nothing element and it's not the whole group itself, you call it a proper subgroup.
A proper subgroup, that's the term.
So going back to our quartz group, D3, which has an order of 6, does it have any proper subgroups?
It has 2. The first is the set of pure rotations around the z-axis. The identity, the 120-degree rotation, and the 240-degree rotation. That forms a complete group on its own, the cyclic group C3. Its order is 3.
And a second.
Is any one of the 180-degree flips plus the identity. That forms a C2 group with an order of 2.
So the big group of order 6 contains a subgroup of order 3 and subgroup of order 2. And there's a theorem that governs this relationship, isn't there?
A hugely important one, Lagrange's theorem.
And what does it say?
It says that the order of any subgroup, let's call it n prime, must be a divisor of the order of the main group, n.
So for our quartz example, 3 divides 6 and 2 divides 6. It works.
It has to. You could never, ever find a subgroup of order 4 or 5 inside a group of order 6. It's mathematically forbidden. And the ratio, n divided by n prime, is called the group index.
This sounds like it has massive physical implications.
Oh, absolutely. Think about a crystal changing its structure because of temperature or pressure, a phase transition. It almost always changes its symmetry.
And it does that by moving from a higher symmetry group,
The supergroup.
down to a lower symmetry subgroup.
And Lagrange's theorem dictates the only possible pathways for that to happen. A crystal with a super high symmetry, say order 48, can't just suddenly drop to a symmetry of order 5. The transition has to follow this strict hierarchical roadmap of permissible subgroups. It's the backbone of how we predict material stability.
Okay, I think we have the theoretical tools. Let's try to build all 32 of them.
Let's do it systematically.
Let's just remind ourselves why there are only 32. Not 31, not 33.
Right. There are 2 big constraints. First, they have to be point groups, so everything intersects at one fixed point. And second, and this is the big one, they have to be compatible with a repeating periodic lattice structure.
The crystal has to be able to tile space infinitely without leaving gaps,
Exactly. Any symmetry that violates that rule is out.
which is why we need to get comfortable with the notation. There are 2 main types, right?
There are. Most of the time, especially in solid-state physics, we'll use the international or Hermann-Mauguin symbol. It's very descriptive, like 32 or m-bar 3 meter.
But sometimes you see the Schoenflies symbol.
Yes, molecular physicists tend to prefer that one. So 32 becomes D3, m-bar 3 meter becomes, oh, we'll try to use both so you get used to seeing them.
And to visualize all this, crystallographers use these diagrams called stereographic projections. How can we picture one of those in our heads?
Okay, imagine your crystal is at the center of a glass sphere. Now, any feature, like the direction an axis is pointing, projects a point onto the surface of that sphere.
So it's a 3D map on a sphere.
Right. But to get it onto a 2D piece of paper, we do a projection. Imagine you're looking down from the North Pole. For every point on the northern hemisphere of the sphere, you draw a line from that point straight down to the South Pole.
Right.
Where that line pierces through the equatorial plane, the flat circle at the equator, that's where you draw your point on the 2D diagram.
What about points on the southern hemisphere?
You do the opposite. You project them up to the North Pole. The key thing is how we mark them. A point from the northern hemisphere is usually a solid dot. A point from the southern hemisphere is an open circle.
And that dot versus circle distinction is what tells us about handedness, right?
It's everything. If an operation, like a reflection, takes a point in the northern hemisphere and moves its equivalent to the southern hemisphere, you'll see a dot turn into a circle on the diagram. It's a visual way of showing that the operation changed the object's handedness from left to right or vice versa.
Okay, I think I can picture that. So step I. Where do we begin building?
With the absolute simplest case, the proper rotations. These are just the cyclic groups, N or Cn.
They just have the identity and powers of a single rotation axis. But the lattice constraint is huge here. Why can we only have rotations of order 1, 2, 3, 4, and 6? Why no 5-fold or 7-fold axis?
This is the famous crystallographic restriction theorem, and the best way to think about it is tiling a floor.
Okay.
You can tile a floor perfectly with no gaps, using shapes with 2-fold symmetry like rectangles, or 3-fold like triangles, or 4-fold like squares, or 6-fold like hexagons. They all tessellate.
But you can't tile a floor with regular pentagons.
You can't. You'll always leave little diamond-shaped gaps. Since a crystal lattice needs to fill all of space perfectly and infinitely, only rotations of 1, 2, 3, 4, and 6 are compatible. 5-fold and 7-fold symmetry are forbidden in periodic crystals.
That tiling analogy makes it so clear. Okay, so in these CN groups, we also have this idea of polarity.
We do. Any odd-order group, like C1 or C3, is polar. The 2 ends of the rotation axis are not symmetrically equivalent. Think of a screw or a cone. The top is different from the bottom.
But the even ones, C2, 4, and 6, are generally 9-polar along that axis.
Correct. And on their stereographic projections for C4, let's say, you would just see 4 solid dots arranged in a circle around the center. All dots, because there's no change in handedness.
Okay, that's step 1. What's step 2? How do we add complexity?
The next logical step is to combine that n-fold axis with a second different rotation, specifically a two-fold axis that's perpendicular to it.
And as soon as you add one, Euler's theorem says you automatically generate a whole set of them.
That's the closure axiom at work again. It has to happen. The resulting groups are called the dihedral point groups. The notation is n2, or dn.
And the ones that are allowed are 2212, 32, our quartz group again, 422, and 622.
Right. And if you try to visualize 422, you have the four-fold axis running up and down vertically, and then you have four separate two-fold axes lying flat in the horizontal plane, kind of radiating out from the center.
Okay, now for step 3, we're going to introduce operations of the second kind, the ones that change handedness.
Yes, starting with inversion. In step 3, we take our n-fold rotation axis and we combine it with a center of symmetry, an inversion point. This creates a new kind of element called a roto-inversion axis.
The notation for that is n bar, right?
N bar, or S2n. The operation is a rotation followed immediately by an inversion through the center point.
And this is where some key equivalencies pop up that, stop the number of groups from exploding.
They do. A 1-bar axis is just the same as simple inversion. A 2-bar axis turns out to be exactly equivalent to a mirror plane. And a 3-bar is the same as a threefold axis with a perpendicular mirror, which we'll get to.
So the only truly unique ones are 1 bar, 3 bar, 4 bar, and 6 bar.
That's it. And if you looked at the stereographic projection for 4-bar, you'd see a point start as a dot, then the first operation rotates it 90 degrees and inverts it, so it becomes a circle in the next quadrant. Then the next operation rotates that circle 90 degrees and inverts it back, so it becomes a dot again. You see this alternating dot-circle pattern.
Very cool. Okay, so that was combining rotation with inversion. What's step 3?
Step 3 is combining the rotation axis with a mirror plane that is perpendicular or horizontal to the axis.
So this gives us the groups n/m or CNH, where H is for horizontal.
Yes. The groups are 2 meters, 3 meters, 4 meters, and 6 meters. The order is always 2 times n. If you picture 6 meters, it's like a hexagonal prism that's been sliced right through the middle by that horizontal mirror plane.
And the stereographic projection would show the 6 dots from the C6 group, plus 6 open circles directly underneath them, reflected across the equator.
Perfect.
So that was horizontal mirrors. What about vertical mirrors?
That's step IV. Here we combine the n-fold axis with n mirror planes that actually contain the axis. They stand up vertically.
And these are the NM or CNV groups.
Right, V for vertical. The order is again 2n. The main groups are 2 millimeters, 3 meter, 4 millimeter, and 6 millimeter.
What's with the double M and 4 millimeter?
It's about orientation. It tells you there are two distinct sets of vertical mirror planes that are not symmetrically equivalent to each other. For 4 millimeter, you have one set of mirrors cutting through the faces of a square prism and another set cutting diagonally through the corners.
Ah, okay. The notation is very specific. What does a CNV group look like?
Think of a perfectly symmetrical cone, or maybe a pyramid. That's the kind of form they generate.
Okay, step V feels like a combination of the last few, combining roto-inversion axes with vertical mirror planes.
It's a very sophisticated blend. These are the groups M bar M or DND, where D means diagonal. The main ones to focus on are 4 bar 2M and 6 bar M2.
And the order of the symbols in the Hermann-Mauguin notation is critical here, isn't it?
It is absolutely critical. It tells you the relative orientation of the symmetry elements. In 4 bar 2, the primary direction has a 4-bar axis. The secondary direction has two-fold axes, and the tertiary direction has mirror planes.
And if you just swap the last two to 4 bar M2, that's a completely different group.
A completely different physical arrangement of the symmetry elements. Yes, the notation is a precise set of instructions.
Wow. Okay, step 6. This feels like we're getting to the highest symmetries now, outside of the cubic system.
We are. In step 6, we create groups that have it all. An n-fold rotation axis, a perpendicular horizontal mirror plane, and coinciding vertical mirror planes.
That's n/m or D and H.
Right. And remember, whenever you have two mirror planes that are perpendicular to each other, you automatically generate a two-fold axis right along their line of intersection. These groups are full of generated elements.
The groups here are 4 millimeters and 6 millimeter.
Correct. Min is short for 2 meter, 2 meter, 2 meters. It has 3 mutually perpendicular mirror planes, and therefore 3 mutually perpendicular two-fold axes. It's the symmetry of a brick.
And 4 millimeters and 6 millimeters just build on that with higher order axes. Their stereographic projections must be incredibly crowded.
They are. They show a very dense arrangement of equivalent points, which is a hallmark of high symmetry.
Which leaves only the final steps. the cubic groups.
The cubic groups. What sets them apart is that they all possess multiple threefold axes. That's the defining characteristic.
And step the seventh is just the pure rotational ones.
Just the rotations. These are groups of the first kind, so they don't change handedness. There are two of them, 23, which has an order of 12, and 432 with an order of 24.
And the threefold axes run along the body diagonals of a cube, right? From one corner to the opposite corner through the center.
That's their defining feature. The 432 group, also called O, also has fourfold axes running through the faces of the cube. It's the symmetry of a perfect octahedron.
And finally, step eighth. We add reflections and inversions to those cubic groups.
And that gives us the final three. We get 4 bar 3, or TD, which is the symmetry of a tetrahedron. We get M bar 3, or TH, both have order 24.
And then we get the last one, the group with the highest possible symmetry in a crystal.
The king of all point groups. M bar 3M, or OO. It has an order of 48. It possesses every symmetry element of the cube. It's the pinnacle of crystallographic symmetry.
And that's it. We built all 32.
That's the complete systematic derivation.
So now that we have them all, we can start to sort them in ways that tell us about their physical behavior. The first big division is into what are called Laue classes.
Right. And this is a very simple division. It's based entirely on one question. Does the group contain an inversion center or not?
So it's centrosymmetric or non-centrosymmetric?
Exactly. Only 11 of the 32 groups contain that inversion operator. Those 11 are the centrosymmetric groups, and they form the 11 Laue classes. The other 21 groups are non-centrosymmetric.
And that lack of an inversion center is a huge deal for material science.
It's the single most important property for many applications because it's a prerequisite for being a polar group.
And what defines a polar group?
A polar group has at least one direction where the two ends are not symmetrically equivalent. If a crystal lacks an inversion center, it's possible for it to have a permanent or inducible electrical dipole moment.
And that is the necessary condition for something like piezoelectricity, isn't it?
It's the absolute requirement. Piezoelectricity is the ability to generate a voltage when you squeeze a crystal. This can only happen in the 10 polar non-centrosymmetric groups.
Right.
Because if you squeeze it, you can shift the centers of positive and negative charge slightly apart, creating a net voltage. If the crystal had an inversion center, for every positive charge that moved one way, a symmetrically equivalent negative charge would move the other way, and everything would perfectly cancel out. No net dipole.
So just by knowing the point group, you can say this material can't be piezoelectric.
Instantly. You've ruled out 22 of the 32 possibilities right off the bat.
Let's talk more about that handedness idea we saw in the stereographic projections. Chirality.
Right. A chiral object is anything that can't be superimposed on its mirror image. Your left and right hands are the classic example.
In terms of symmetry, what does it mean for a crystal to be chiral?
It means its point group lacks any operation of the second kind. No mirror planes, no inversion center, no roto-inversion axes. It's made up purely of rotations.
And this leads to a phenomenon called enantiomorphism.
Yes, that's the relationship between the left-handed form of a crystal and its right-handed form. Quartz is the most famous example. You can find left-handed quartz and right-handed quartz crystals.
And they have different physical properties.
Only one specific kind. They rotate the plane of polarized light. One form will rotate it clockwise, and its enantiomorph will rotate it counterclockwise by the exact same amount. This optical activity is a property exclusive to the chiral groups.
Now, all of these rules are great, but for modern science, we need to be able to use them in computers. That brings us to the matrix representation of the groups.
Yes. Every single symmetry operation can be perfectly described by a 3x3 matrix. That matrix, D, is a mathematical instruction that tells you how to transform the coordinates of a point, xyz, to its new position, xyz.
So for our quartz group, with its 6 operations, there are 6 corresponding matrices.
There are, and the set of those 6 matrices is isomorphic to the abstract group itself. The identity matrix, D0, is just ones on the diagonal and zeros everywhere else.
And what about, say, the 120-degree rotation around the z-axis?
That matrix would have cosines and sines of 120 degrees in the top left corner to mix the x and y coordinates, and a 1 in the bottom right to show that the z coordinate doesn't change.
And the beauty of this is that the matrix math has to follow the group's multiplication table.
It has to. If you take the matrix for the 120-degree rotation and multiply it by itself using the rules of matrix multiplication, the resulting matrix will be the matrix for the 240-degree rotation. It's how we verify the structure and how computers can work with these abstract symmetries.
We touched on this before, but let's revisit the hierarchy of these groups, the group-subgroup relations.
Right. You can actually draw a huge, complex chart that shows how all 32 groups are related. It shows every possible pathway of descending in symmetry from a supergroup to a subgroup.
And this is literally the roadmap for phase transitions.
It is. A crystal might exist in a high symmetry tetragonal phase, say 4 millimeter, but if you change the temperature, it might distort slightly. It loses a few symmetry elements and falls into a lower symmetry subgroup, maybe.
And that descent isn't random. It has to follow the paths on that chart.
And critically, when it loses symmetry, it can gain new properties. If a crystal transitions from a centrosymmetric supergroup to a non-centrosymmetric subgroup, it might suddenly become piezoelectric. Understanding these relationships allows us to predict and even design materials that gain specific functions during a phase change.
Okay, let's get practical. To build a model of a crystal, we need to know where the atoms actually sit. This brings up the idea of a general position.
A general position is any random point, x, y, z, inside the crystal that does not sit on a symmetry element, like a mirror plane or a rotation axis.
And if you apply all the operations of the point group to that one single point,
You generate a whole set of symmetrically equivalent points. That set is called the orbit.
and the number of points in the orbit, let me guess, is equal to the order of the group.
Always. For the high symmetry M-bar 3-meter group, order 48, a single atom in a general position means there must be 47 other identical atoms at positions dictated by the symmetry.
But atoms don't always sit in random spots. They often sit on the symmetry elements themselves, a special position.
Exactly. And when a point moves from a general position onto a special position, something interesting happens. Some of the symmetry operations now map that point right back onto itself.
So the number of equivalent points, the multiplicity goes down.
It goes down, and the point itself now has a higher symmetry than before. We call that its site symmetry.
Let's use the example of 4 millimeter, which has an order of 16. A general position gives you an orbit of 16 points.
Right. But now let's move that point so it lies on the main fourfold rotation axis, the z-axis. Now, rotating by 90, 180, or 270 degrees around that axis leaves the point's position unchanged.
So a lot of those 16 points collapse into one.
They do. In fact, that orbit of 16 points collapses down to just two. One at 0, 0, 0, 0, and another at 0, 0, minus 0, related by the horizontal mirror plane. The multiplicity drops from 16 to 2, and the site symmetry of that position is now 4 millimeter. Knowing an atom's site symmetry is crucial for understanding its chemical bonding and its physical environment.
Now, before we wrap up, it's worth mentioning that there are symmetries that don't fit into our 32 crystal groups.
Yes, the non-crystallographic groups. These include things like five-fold symmetry or the icosahedral symmetry you see in viruses and buckyballs. They're perfectly valid point groups, but they can't form a periodic, repeating crystal lattice.
Okay, so looking at the 32 that are allowed, the real-world statistics of which ones are most common is really surprising. You'd think nature would favor the highest symmetry.
You would. You'd expect the most perfect group, bar 3M, to be everywhere. And it's important. It's the symmetry of things like diamond and copper, but it only accounts for about 6 or 7% of known inorganic crystals.
The actual winner, by a landslide, is one of the simplest, lowest symmetry groups.
It's the monoclinic group 2 meters, just a single two-fold axis and a single mirror plane. Order of 4. And yet it accounts for over a third of all known inorganic compounds and almost half of all organic compounds.
Yeah, that's a stunning dominance. It really shows nature isn't always optimizing for pure geometric perfection.
Not at all. It's optimizing for energetic stability.
Just to circle back to the computational side one last time, we talked about generator matrices being a shortcut.
Right. You don't need 32 different sets of matrices. You can mathematically generate all 32-point groups using a minimal set of just 15 fundamental 3x3 generator matrices.
How's it work?
A computer starts with, say, the matrix for a two-fold rotation and the matrix for an inversion. It multiplies them together to get a new matrix. Then it multiplies all the combinations until no new, unique matrices are produced. At that point, the set is closed, and it has generated a complete point group. It's how all modern crystallography software works.
So we've been focused on 3D. What happens if we reduce this all down to 2 dimensions? For things like surface science or graphene?
When you move to 2D, you have to throw out any symmetry operation that moves you out of the plane. A horizontal mirror plane, for instance, becomes meaningless.
So the number of possible groups must drop dramatically.
It does. You're left with only 10 possible 2D crystallographic point groups, and those 10 are only compatible with the 3 possible 2D lattice types: oblique, rectangular, and hexagonal.
It's just amazing how this entire mathematical framework, which seems so abstract, underpins everything.
Yeah.
And we should probably give a nod to the person who invented it,
We absolutely should. The French mathematician Évariste Galois,
who came up with the foundations of group theory in his late teens.
and was tragically killed in a duel at age 20. His work was so far ahead of its time, it was only truly understood and formalized years after his death. It's an incredible story. This abstract math, created by a young genius, turned out to be the essential language needed to describe the fundamental structure of the physical world.
So when we step back, what does this all mean?
It means we've taken a journey from 4 simple mathematical axioms: closure, associativity, identity, and inverse, and use them to systematically build the entire set of 32 rules that govern how atoms can be arranged symmetrically in a crystal.
And knowing a crystal's point group is the key.
It's the key. It tells you about its local atomic environment, its potential for polarity, and therefore its ability to have properties like piezoelectricity or optical activity. And the matrix representation is what lets us use computers to design new materials based on these very principles.
Okay, so a final thought to leave you with, circling back to those population statistics. We learned that the most geometrically perfect group, M bar 3M, with its 48 symmetry operations, is actually quite rare. Meanwhile, the humble, low-order monoclinic group 2 meters, with only 4 operations, is by far the most common symmetry in the natural world. So if nature isn't always striving for maximum symmetry, what is it optimizing for?
The answer seems to be energy. Often, a small distortion that breaks high symmetry allows the atoms to settle into a more stable, lower energy configuration. It's a trade-off. Nature gives up a little bit of geometric perfection to gain a lot of practical physical stability. And that constant tension, that push and pull between perfect symmetry and energetic reality, is the true engine that drives the growth of every crystal you've ever seen.